Welcome to Regulated Power Supplies, Part 10. All right, so here's where we left off in the last video. We're working on the op-amp regulated circuit. And we calculated R3 and R4 and found that we get an expected range of 4.511 volts to 25.49 volts. In the last video, we determined that our V plus pin on our op amp was going to be 30 volts, and that was as much as we wanted to go for the LM741, and that would enable us to have the up to 25 volts on the output. But we need to design the actual power supply for the op amp for that 30 volts. So I've got the absolute maximum ratings from the data sheet, and it references an output short circuit duration. And you can see where we can short the output of an op amp for, they've got it labeled as continuous, but you can just short it for as long as you want and it's going to be okay. And that's what's going to help us or enable us to do this fixed current limiting. Additionally to that, later on in the data sheet, and I've clipped it out here where it's got the output short circuit current, and it's listing that as 25 milliamps. So what we want to do is design a power supply for the op amp, the V plus supply for the op amp, to be able to run at 30 volts. And we need basically we design for more current than what we need, because the op amp is going to ask for as much current as it wants. And according to the data sheet, it's never going to ask for more than 25 milliamps. But we don't want to have a situation where we've got the supply for the V plus designed for like 15 milliamps, if you would, and then when the op amp needs 15, the whole regulation falls apart. So we designed for a little bit more than what it would ever want. So we're going to set our IEQ3, the current for the V plus pin, to be 30 milliamps, 5 milliamps above what the maximum would ever need to be. So now that we've got our IEQ3 of 30 milliamps, and that's what we're going to, our supply current for our maximum supply current for the op amp, we can then design the R1 and R2 branch. So if we divide that current 30 milliamps by the beta of the Q3, which is a 2N5088, so divide that by 301, that gives us an IB, a base current for that transistor, of 99.668 microamps. And just like all of our regulation, we're going to want that IR2 current to be 10 times, a minimum of 10 times bigger than the IBQ3. It gives us an IRQ of minimum of 996.678 microamps. We know what the voltage is at pin 3. We've got the VZ of 3 volts, and we know that we've got 30 volts on pin 7, so that gives us 30.7 from the base to ground of Q3. So we know that VR2 is 30.7 volts minus the 3 volts of the Zener, giving us a 27.7 volt drop across R2. So now that we've got the voltage VR2 and the current IR2, we can calculate for an approximate R2, and we get an R2 of 27.792 k ohms. So just like before, we're going to round that down to the next standard value. That gives us a 20 k ohm resistor. We can calculate power in that for that resistor at V squared divided by R, and we get a power of 28.48 milliwatts. All right, so now that we've got our standard value at 27K for R2, we can go ahead and divide the voltage by that standard value and get our actual IR2 of 1.025 milliamps. Again, that's more than 10 times the IB of Q3. We're going to add those together to solve for the current of IR1, and that gives us the 1.125 milliamps for IR1. Now we're going to take our VR1 is going to be equal to the VC max, the capacitor voltage when it's fully charged, minus VR2 minus VZ. That gives us a VR1 of 10.333 volts. Dividing that by IR1, we get an R1 value of 9.185 k ohms. All right, so here's the problem. Our R1 is not a standard value, and technically we may still see some ripple voltage across R2. So we're going to do the same thing to correct that problem as we did in previous versions whenever we had that issue. So we're going to add another Zener. Okay, so we know that we want that voltage in that what was R2 position to be 27.7 volts all the time. Ideally all the time. It just sits there at 27.7 volts. And I looked up in Mouser and was able to find a Zener that is rated at 27.7 volts. And from that, though, we also need to know at that Zener what the IZM and IZK are. So I've got we're calculating the same as we did for the other Zener. It's 500 milliwatt, so it's the same series as Z1, same family. And we've got an IZM of 18.05 milliamps and an IZK of 0.5 milliamps, which was the same as Z1. So we've through that branch, we're going to need at least 0.5 milliamps to keep those two Zeners regulated. All right, so now that I've got my IZM and my IZK figured out, I want to go ahead and build another. We did this in previous videos where we're trying to find out what the VC min is going to be. We want to know with that 2,200 microfarad capacitor, what is our minimum voltage? What's our ripple look like? And we're using the same formula that we always use, the VC equals V final minus quantity V final minus V initial e to the negative time over tau. Now our tau, our C we know of 2,200 microfarad, we're using the same cap we had used previously. And we want to know what is our maximum current that we're going to see, what that capacitor is going to see. Okay, and so we know that we designed the thing for 0.5 amps on the output. So we know basically at the collectors of the Darlington pair, there should be 0.5. We've got the Q3 transistor that's going to provide a maximum of 30 milliamps. And now we've got our IR1 branch, and we know that that's got to be a maximum of IZM. So if we add all those up, we get a maximum current of 0.548 amps. And we're probably going to be less than that in reality, but this gives us resistance to work off of. So we know what our VC max was. Divide that by whatever the max current is there. That is our REQ. And I calculated an REQ of 74.871 ohms. And now we can use that number in our VC min formula. And we've got 8.33 milliseconds because it's a full wave rectifier. And punch in the numbers there, and we get a VC min of 39 volts. All right, so now that we've got VC min, we can go ahead and solve for VR1 min. So we want to find when that voltage is the minimum there. And we get a formula of VC min minus VZ2 minus VZ1. And we find that VR min is 8.3 volts. Now to solve for R1, we want to divide that VR min by 2 IZK. So we want to make sure that we've got enough current through there on the minimum portion of the discharge cycle to keep those two Zeners biased. So we're going to use 2 times IZK, and that gives us 1 milliamp. And we're going to divide the 8.3 volts by the 1 milliamp and get 8.3 k ohms. just not a standard value, so we need to round that to the next standard value. Okay, so we've got our R1 set to 8.2K ohms. And we need to check one other thing before we call it good, and that is to make sure that we're not exceeding our IZM. So we want to think of the power cycle, or on the discharge or charge cycle of the capacitor, we want to look at it at VC max. And so we know that that's going to be 41.033 volts there. We're going to subtract off the Zener voltages, and we know that VR1 max is going to be 10.333 volts. If we divide that by the 8K, we end up with 1.26 milliamps. So we know that already that's less than an IZM of 18 milliamps, and so we are good to go. The actual IZ is going to be IR1 max minus the IBQ3, so it's going to be something just less than that 1.26, and those diodes can handle that current all day long. Okay, so we've got the voltage, variable voltage branch R3, RV1, and R4 designed and built. We did that in the previous video. Now we've got a really nice stable voltage for our op amp, and we've got R1 designed. We've verified that our ripple voltage is good. Then the final thing for this fixed current regulated circuit is going to be calculating R5, and we're going to do that in the next video.